When we left off in the last topic, we had looked at how there were these 6 leptons. They were very small, they'd never been divided, and there weren't that many of them. So the argument that they were fundamental was pretty strong. However, the hadrons, there were hundreds of them. They were pretty heavy. We hadn't been able to divide them, but something just kind of seemed off here, right? Maybe there was something more fundamental and it was different combinations that were making all the hadrons. So that is exactly what was proposed. They arrived at it independently. They weren't working together, but 2 physicists, Murray Gell-Mann and George Zweig, they came up with this idea that protons and neutrons, and all of the hadrons, but in Physics 30 we focus on protons and neutrons, were not fundamental. Remember, protons and neutrons have been fundamental particles since we knew about them. This was a big deal that they were suggesting this. People weren't on board right away. And what they had proposed was that these protons and neutrons were actually made of simpler particles that were actually fundamental, called quarks. Of course, no one had actually seen quarks, observed them, but they came up with the properties that quarks could have, and using those properties, Gell-Mann and Zweig were able to show that you could make every single known hadron with a certain combination of these quarks that they had proposed. You might be saying, okay, but anyone could do that. They could just make up some random particle that works out properly to give you the right hadrons. But where their theory really started to pick up some momentum was when they looked at all the combinations of quarks. They could predict different hadrons that might exist that hadn't been discovered yet. And sure enough, we found those exact hadrons later. And so physicists started to say, maybe there is something to this quark idea. And so experiments started to look at this, and where this quark model became undeniable was when we shot high energy electrons at protons, And the results should seem pretty familiar to you. You should have some deja vu here. It looked a lot like Rutherford's gold foil experiment, except obviously now on a smaller scale. Because what was happening is not all of the electrons were feeling attraction towards the proton. Some electrons were actually getting repelled depending which part of the proton they were kind of incident upon, right? An electron being repelled by a proton, that goes against everything an electron stands for, right? It's supposed to be a positively charged particle. So you can only explain this if the positive charge is not evenly distributed, but instead concentrated in 3 centers. Hey, see how this sounds a lot like Rutherford's gold foil? The same way we found out that the positive charge was not evenly distributed like in the plum pudding, but instead concentrated in the nucleus, With the quarks, you could explain this because the charges of quarks that go to make a proton, you have 2 positive ones and 1 negative one. So hey, that would repel the electrons if one of the quarks inside a proton actually has a negative charge. And so hadrons are not fundamental. Protons and neutrons are not the end of how far you can break those down. You can break them down further. They are made of quarks. One of the big issues, one of the reasons people had thought quark theory was too weird, one of the weirdest things about the quarks, one of the main reasons people didn't want to get on board with them, was that they have fractional charges. And you might be saying, oh wait, so the quantization of charge is not into the elementary charge? You could make the argument that I guess it is into 1/3 the elementary charge, but I'm going to say that it is still quantized in the elementary charge, and you'll see why in a second here when we talk about the binding of them. So what keeps those quarks together? Well, it's our old friend, the strong nuclear force. As a matter of fact, that's mainly what the strong force's purpose is. The binding of quarks is actually what the strong force is all about. Yes, it binds nucleons, but that's kind of a side effect, realistically. We actually even call that the residual strong interaction. Residual, kind of like it spills out over, it's kind of leftover, it's extra. And it's because the strong force binding quarks in one nucleon can affect the quarks in a neighboring nucleon. That's how strong the strong nuclear force is. And really what it's doing is binding quarks. And if there's more quarks nearby in another nucleon, well, okay, it'll help kind of bind the nucleons together. So that incredibly strong force that's holding every nucleus together is actually just kind of a side effect of the main purpose of the strong force, which is to bind quarks together within the proton. Now, I'm going to return to what I said about how I would still say it's fair to say that charge is quantized into the elementary charge, 1.6 times 10 to the negative 19, and not 1/3 of that. The reason is that, recall that to overcome any force, you need energy, right? You have to put a lot of energy into the system to overcome a very strong force. The binding of quarks by the strong force is such an incredibly strong interaction that if you were to try and pull 2 quarks apart in a baryon, such as a proton or neutron, you would have to put in so much energy that by E equals mc squared is equal to the mass of a new quark. So you can try and split quarks, but the amount of energy required to do that will just immediately create new quarks that will then go and bind. For this reason, the idea of a free quark, a quark not bound within a baryon, is nonsense. They don't exist. There is no such thing as a free quark. They will immediately bind to make some kind of hadron, either a baryon or a meson. So yes, they are fundamental particles, but they do not exist on their own. They will always bind to form some type of hadron, either a baryon or a meson. And so for that reason, yes, even though the quarks might have a fractional charge, they're always together to form something that has an integer charge. And so if you ask me, charge is still quantized into the elementary charge. But you could make the argument that it's actually quantized into 1/3 the elementary charge. I wouldn't fight you too hard on that. Okay, so just kind of an analog, a comparison in the electromagnetic force to this residual strong force, just to make you a little more comfortable with that idea. Think about molecules, right? The electromagnetic force, what's the main thing it's doing? It's binding electrons to protons in individual atoms. But there's some spillover, and the oppositely charged parts of different atoms can come together to make a molecule, right? Same idea is kind of happening in a nucleus, but on a way smaller scale. You have quarks bound together by the strong force, and then bigger picture, some spillover strong force is now binding the nucleons, all containing quarks, together through that interaction. Okay, and it worked out incredibly beautifully well. It's one of those things where you just kind of have to sit back and go, wow, the weirder the universe gets, the more it actually starts to make sense, right? There are 6 types of quarks plus their antimatter versions, just like leptons. And there we go. We've solved that very strange, just off feeling issue from before where we had 6 leptons, but hundreds of hadrons. Okay. Now, don't get me wrong. There's still hundreds of hadrons. It's just that the hadrons aren't fundamental. They're made of more fundamental particles called quarks. And so all matter is actually made up of not protons, electrons, and neutrons, though it is. But if you want to keep going, what all matter is made up of is quarks and leptons. And then there are the fundamental bosons, which carry forces. Okay, so we think of all matter as being quarks and leptons, and then fundamental bosons are kind of like the glue that keeps the matter together. So the 6 types of quarks, the only ones you need to know in Physics 30, and this goes for all types of matter, is the first generation, which are the ones you already know anyway, so don't worry. The only new ones here are the quarks. But those are the up quark and the down quark. Notice in the second generation, strange and charm, everything stays the same about the charge and all that, they just get bigger. And then in the third generation, same thing, the bottom and the top quark, same charges, just heavier masses. So these are on the back of your formula sheet, the up and down quarks and the masses, and they are all the Physics 30 curriculum actually requires you to know how to use. So what does it look like? Now, in all baryons that we know, there are 3 quarks, though technically there's nothing stopping there for being 5 quarks or 7 or 9, an odd number of quarks. However, all baryons we know only have 3 quarks. And they are bound by the force-mediating particle of the strong force, gluons, which again just carries the strong force. Remember quantum electrodynamics, that they use photons as force carriers for the electromagnetic force? There's something called quantum chromodynamics that describes gluons doing this. Chromo means color, and without getting too much into it, just like particles can have electric charges or masses, quarks can have something called a color. Of course, it's not a real color. We just had to give it names to describe it. Same goes for up and down, right? There's nothing uppy or downy about them, but we gave them the colors red, blue, and green, and then obviously anti-red, anti-blue, and anti-green. And one of the things we've noticed is that you always must have them add up to be colorless or white. So red, green, and blue, if you combine those 3 colors, you will get white. So in a baryon with 3 quarks, you must have a red, a blue, and a green. Always. They can change between them, but it must remain color neutral. That also goes back to why you can't separate them. You can't have a free color charge, okay? The why of that is an ongoing question. So maybe you come back in a few years and you can tell me about it after you've done some research. So gluons help mediate that by being the force carrier of the strong force. Anyway, again, all beyond Physics 30. I'm just giving you a bigger context here so you can kind of see. Don't panic about remembering all of this stuff. Okay, mesons, again, these aren't required for you to know, but it does help with understanding how fundamental quarks are. So all mesons are just made of some quark and an anti-quark. Okay, so you could have an up quark and an anti-down quark, or an up quark and an anti-strange quark. These still conserve color because you have blue and anti-blue, right? You could have red and anti-red, or green and anti-green. We don't call it yellow. So now you see, yes, leptons and hadrons, but really hadrons are all made of quarks. All right, all stable matter is made of first-generation quarks and leptons. Baryons are made of 3 quarks. With this information, confirm that the diagrams for the nucleons above are correct. So we have our proton and our neutron. So even without knowing what quarks are, just having the back of your formula sheet, you should be able to work out the answer to this question if you put some thought into it, okay? So how do we confirm that the diagrams are correct? Well, what do we know about protons? I'm going to say right off the bat, do not use mass to do this. Most of the mass of a proton actually comes from the energy involved in binding quarks, okay? So do not use mass. However, you can use something else. You can use charge, okay? Or physics principle number 7. So if we were going to make a proton, I want you to look at up quarks and down quarks and see if you can find a combination that will give us the charge of a proton. So we have plus 2/3 and minus 1/3 to work with. We know we're going to use 3 of them, and we got to figure out how to make that equal plus 1, like a proton, right? So if we did plus 2/3 plus 2/3 plus minus 1/3, we would get, well, 2/3 plus 2/3 is 4/3, minus 1 is 3/3, positive, right? Which equals plus 1, like a proton. And what is plus 2/3? Which quark? That is up, up, and minus 1/3 is down, right? So the recipe for a proton is an up quark, and a down quark, which is exactly what this said. Plus 2/3, plus 2/3, and minus 1/3 gives you plus 1 of the proton. That's where the proton's charge comes from. Okay, let's look at the neutron now. They're saying up, down, down. Let's see if we can get there on our own, but we have 2/3 to work with and minus 1/3 to work with. We need to get to 0. Well, there's a pretty clear path for us, right? We have plus 2 and 2 minus 1s. So 2 minus 1 is 1, minus another 1 is 0. Just like a neutron. So what's the recipe for a neutron? Up, down, down, quark. Okay, we already answered that one. Which one did we use? Number 7, conservation of charge. What quarks would an antiproton be composed of? You need to get to minus 1, right? But I want you to think about antihydrogen like we've talked about, right? How did you make antihydrogen? You took all the stuff that makes hydrogen, a proton and an electron, and built it with the anti version of that, right? An antiproton and an anti-electron would make antihydrogen. So just having a charge of -1, you could technically do that with a down, down, down quark, right? But that's not an antiproton because an antiproton is made of all the stuff that makes a proton. So how do you make an antiproton? With an anti-up, and an anti-down. You can confirm with the charges there, right? What would the charge of an anti-up quark be? Well, instead of positive 2/3, negative 2/3, right? What would the charge of an anti-down be? Instead of negative 1/3, positive 1/3. So you have negative 2/3, negative 2/3, that's negative 4/3, plus 1/3 is negative 3/3, negative 1, just like the charge of an anti-proton. How do you make an anti-neutron? Figure out how to make a neutron, which we just did, and then anti-everything. So an anti-up and 2 anti-downs. What would be the charge of a baryon having the quark structure UUU? So up, up, up. Well, take out your formula sheet, look on the back, find the up quark, and you'll see that they have a charge of plus 2/3 E. So it's going to be, which gives us 6/3 positive, which is the same as plus 2. Okay? That's how you can find whether a combination is possible or not. It needs to come up with an integer charge overall. So 0, 1, -1, -2, whatever. Okay, so technically, should you memorize this? Yes. But if you think about it and you use the charges on the back of your data sheet, you can always get there, right? You can always work this out. And when I say memorize, I'm just talking about nucleons. So protons and neutrons. So you got to remember up, up, down, and up, down, down. Quarks can really let us see beta decays in a new light too, okay? So again, what's happening in a beta negative decay? Well, in a beta negative decay, a neutron needs to become a proton, and to conserve charge, since something neutral is becoming something positive, you better make something negative to cancel out that new positive and bring you back to neutral, right? So as words, we had a neutron becoming a proton, an electron, and don't forget the electron antineutrino, okay? But in terms of quarks, we now know that a neutron is up, down, down, and a proton is up, up, down. So now instead of kind of saying, oh, magically a neutron became a proton, we can do it with a little bit more depth, although we still kind of have have a little bit of magic here. But now we can say, okay, well, really what happened is that a down quark became an up quark. And as soon as a down quark becomes an up quark, you have no longer a neutron, but a proton. This is where our weak force comes in. The mediating particles being those W and Z bosons, they act on quarks and leptons. The action of those W and Z bosons causes the down quark to become an up quark through the emission of an electron and an antineutrino. Or to be really proper about it, it's through the emission of a W boson, which then decays almost immediately into an electron and an antineutrino. Okay, and we can check our work with charge conservation. So we had a neutron become a proton, an electron, and an electron antineutrino. The charges of all of those things still need to work out, right? So up plus 2/3, down minus 1/3, down minus 1/3. Okay, that's going to give you overall 0 charge. Just like we know a neutron to have. It's going to become a proton, which is up, up, down. So plus 2/3, minus 1/3, which works out to plus 1. Hey, that's exactly the charge of a proton. Okay, electrons are leptons. They are not composed of quarks. Electrons are fundamental. And so they just have a charge of minus 1. And neutrino, the name means little neutral one, right? So 0. And there we go. Conservation of charge works out. Okay, so this is beta negative decay in the quark model. Yes, a neutron becomes a proton, but more fundamentally, a down quark becomes an up quark. And, do you see the mistake there? That's not a neutrino. That should be an antineutrino. Okay, the E means that it's an electron neutrino, which is just one of the flavors of neutrino. Okay, not being funny, they are called flavors. And so that charge is conserved, you have an electron leaving, right? Because you can even just isolate this and see that, okay, charge is conserved, because from negative 1/3 to positive 2/3, that's a total change of plus 1, right? To get to 0 and then 2 more thirds. So to cancel that out, you need the negative electron. What's doing this again? The weak force is carrying that out with its force carrier bosons. Again, you don't need to know too much about those, but just for a deeper picture. Okay, beta positive, pretty much the same idea, right? But now an up quark is going to become a down quark because up, up, down makes a proton, up, down, down makes a neutron. So turn an up quark into a down quark, and there you go. Just make sure you emit a positron. Oh my goodness, look at this. This should be a positron. I should have checked this diagram better. Okay, a positron and a neutrino, not an antineutrino, a neutrino. Okay, same idea. You can check the conservation of charge and it still works. And this describes beta decay. So just don't forget the big picture of beta decay too, right? You have some nucleus becoming some other nucleus because you have some neutron becoming some proton. And now we can even go deeper and say, because you have some down quark becoming an up quark. Okay, if you really wanted to get fancy, through the action of W bosons and the weak force. So just kind of a mini summary so you can see where we are here, right? How far have we really zoomed into the structure of our universe? Well, you're made of molecules, right? Molecules are made of atoms. Atoms are made of protons, neutrons, and electrons. And for a long time, we thought that's where it ended. And then we realized, wow, even protons and neutrons are not fundamental. They are made of quarks, okay? Electrons are still fundamental. They are leptons. Leptons are fundamental. Mind you, physics teachers were standing in front of their class saying the same thing about protons and neutrons not too long ago. So who knows? Maybe one day I will have to eat my words here. But as of now, how about that? Electrons are still considered fundamental, and evidence that they are has only gotten stronger over the years. Okay, so carbon-14 undergoes radioactive decay to become nitrogen-14. Write the decay reaction in terms of the nuclei involved. Okay, so we have carbon-14. Didn't tell us what type of decay, so let's just go ahead and write our daughter nucleus. And then we can work out, okay, what's missing. So conservation of nucleons, we're actually good, but conservation of charge, we have 6 here and 7 here, so we need something that's going to take away one charge without adding any nucleons. I know just the thing. A beta negative particle, aka an electron. But whenever beta negative decay happens, there's an antineutrino too, right? Okay, now let's do it in terms of the nucleons involved. So really, how did carbon-14 become nitrogen-14? Well, it got one more proton, right? You can think that's what that Z is number of protons or number of positive charges. So it got one more proton. What became a proton? A neutron. So if we wanted to write it in terms of the nucleons, a neutron, which is a nucleon with a charge of 0, became, well, a proton. That's where the extra proton is there, which is a nucleon with a charge of +1. How was charge still conserved? Because it isn't right now. Oh, right, we made a beta particle and an antineutrino still. Okay, so we're just kind of zooming in. We're saying, yes, this happened, and these were observed there, right? But that's because this happened and also made these. And now we're going to even take it one step further and say, do it in terms of the quarks involved. So yes, this happened, but what happened inside of them to make that happen? Well, inside of them, this happened. We had a neutron, which again is just an up, down, down, which became a proton, which is a up, up, down. How did it do that and still conserve charge? With those guys. We don't really use our A and Z format with these, but you still would check the conservation of charge, okay? And I encourage you maybe go ahead and do it. You'll find that the charge of an up, down, down is 0, and the charge of an up, up, down is +1. So how is charge conserved? Well, +1 and -1. A charged hadron moves clockwise through a magnetic field into the plane of the page. So when it enters this, it moves clockwise. So that's like this. So what's this question really asking us to do, right? Yes, it's asking us to predict the possible quarks, but it's a good skill to be able to break that down and say, okay, question, what do you really want from me? Well, to predict the possible quarks, really what we're saying is predict the charge, essentially, right? All adding quarks does is give us different charges. I mean, yes, it gives us all hadrons, but realistically, what's the differences that we care about them for? Just their charges. So what is the charge of this thing? So take out your left and your right hand and see which one works. And I'm getting that if I put my left hand's fingers into the page and point my thumb this way, that works pretty well. The force goes like this and causes circular motion. So you'll only ever have to use the first generation of quarks. That's all we cover in Physics 30. And here's the other thing. Since it's a stable particle, you already know it's the first generation. The second and third generations of matter are unstable. They decay to the first generation very quickly because of their big masses, okay? But even if we didn't know that, unless the question specifically says something about a strange charm top or bottom quark, don't even touch those ones. They're not on our data sheet anyway. Okay, so using up and down quarks, how can we make a negative particle? So we know up, up, down won't do it. That's a proton. We know up, down, down won't do it. That's a neutron. We know up, up, up obviously won't do it because that's going to be +2. There's only one way to do this. Down, down, down. Now that's using matter. That's it. That's the only one. That would give us a charge of -1. Okay. What about using antimatter though? Now we have a couple more options. We could make an antiproton. That would have a negative charge. We could also do 3 anti-ups for in charge of -2. But that's basically it, right? You can try different combinations. Shouldn't be able to find any other ones. And so we've arrived at the standard model of matter, the current understanding of all of the fundamental building blocks that go into matter and its interactions, the basics of what our universe is made out of. Everything that you think of when you think of matter, okay, is here. All matter is made out of protons, electrons, and neutrons, they used to tell you, right? Because that works for pretty much everything, unless you're a particle physicist. Well, protons and neutrons are up and down quarks, and electrons are electrons, obviously. Okay. Now, realistically, everything that is stable is also what I just circled, the first generation. Okay. But the second generation particles have very similar properties as their first generation counterpart. So, for example, the charm quark is a lot like the up quark. The muon is a lot like the electron, except you'll notice the masses all increase. So masses increase from generation 1 to 3, and the stability super decreases. They all exist for like 10 to the -20 seconds, okay? And it's because of the mass. That's not just like a fun fact. It's because of the mass that they become so unstable. What do they decay into? For the most part, their first generation counterpart, right? So charm quarks will decay into up quarks. Top quarks will decay into up quarks. Bottom quarks will decay into down quarks, okay? Tau particles decay into electrons. Muons decay into electrons. And so everything that is matter that you can touch is a quark or a lepton. Even the super unstable ones, they still fit into those two categories. Then we have the stuff that allows matter to interact with each other, okay? Those are the interaction and force carriers, okay? Now the ones that carry force are called gauge bosons. And we've seen these, right? The gluon mediates the strong force. The photon mediates the electromagnetic force. The W and Z bosons mediate the weak force. They are called vector bosons because they mediate, well, things that are vectors, right? Notice gravity is not part of the standard model. One of the biggest challenges of physics today is working gravity into the standard model. That's a job for you folks, okay? There is one final piece of the standard model that we have completely neglected up to this point. Again, you don't really need to know this, but to give you a picture of the grand scheme of things, okay? This particle was actually discovered when I was in grade 12 taking physics 30. It was very exciting. I still remember the day when it happened. The Higgs boson. I shouldn't say it was discovered. It was confirmed to exist. What does the Higgs boson do? Well, to put it very simply, it is the excitation of the Higgs field, which in quantum field theory is the field that interacts with the fundamental particles to give them mass. So why does an electron have mass? Because of its interaction with the Higgs field. Why do quarks have mass? Because of their interaction with the Higgs field. The Higgs boson is the particle representation of the Higgs field, just like the photon is the particle representation of the electromagnetic field. Okay, I'm going to show you a quick video that summarizes this up in a nice way, goes through all of them. Okay, again, do not stress too much about remembering leptons versus hadrons versus bosons. This is so you can contextualize what you're learning about into the bigger picture of things. What you really need to know is just how to put quarks together to make protons and neutrons in terms of this lesson.
If you were to take any everyday object, say a coffee cup, and break it in half, then in half again, and keep carrying on, where would you end up? Could you keep on going forever? Or would you find a set of indivisible building blocks out of which everything is made? Physicists have found the latter, that matter is made of fundamental particles, the smallest things in the universe. Particles interact with each other according to a theory called the Standard Model. The Standard Model is a remarkably elegant encapsulation of the strange quantum world of indivisible, infinitely small particles. It also covers the forces that govern how particles move, interact, and bind together to give shape to the world around us. So how does it work? Zooming in on the fragments of the cup, we see molecules made of atoms bound up together. A molecule is the smallest unit of any chemical compound. An atom is the smallest unit of any element in the periodic table. But the atom is not the smallest unit of matter. Experiments found that each atom has a tiny, dense nucleus surrounded by a cloud of even tinier electrons. The electron is, as far as we know, one of the fundamental, indivisible building blocks of the universe. It was the first standard model particle ever discovered. Electrons are bound to an atom's nucleus by electromagnetism. They attract each other by exchanging particles called photons, which are quanta of light that carry the electromagnetic force, one of the fundamental forces of the Standard Model. The nucleus has more secrets to reveal, as it contains protons and neutrons. Though once thought to be fundamental particles on their own, in 1968 physicists found that protons and neutrons are actually made of quarks, which are indivisible. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up. The nucleus is held together by the strong force, another fundamental force of the Standard Model. Just as photons carry the electromagnetic force, particles called gluons carry the strong force. Electrons, together with up and down quarks, seem to be all we need to build atoms and therefore describe normal matter. However, high-energy experiments reveal that there are actually 6 quarks: down and up, strange and charm, and bottom and top. And they come in a wide range of masses. The same was found for electrons, which have heavier siblings called the muon and the tau. Why are there 3 and only 3 different versions of each of these particles? This remains a mystery. These heavy particles are only produced for very brief moments in high-energy collisions and are not seen in everyday life. This is because they decay very quickly into the lighter particles. Such decays involve the exchange of force-carrying particles called the W and Z, which, unlike the photon, have mass. They carry the weak force, the final force of the Standard Model. This same force allows protons and neutrons to transform into each other, a vital part of the fusion interactions that drive the sun. To observe the W and Z directly, we needed the high-energy collisions provided by particle accelerators. There's another kind of standard model particle called neutrinos. These only interact with other particles through the weak force. Trillions of neutrinos, many generated by the sun, fly through us every second. Measurements of weak interactions found that there are different kinds of neutrinos associated with the electron, muon, and tau. All these particles also have antimatter versions, which have the opposite charge but are otherwise identical. Matter and antimatter particles are produced in pairs in high-energy collisions, and they annihilate each other when they meet. The final particle of the standard model is the Higgs boson, a quantum ripple in the background energy field of the universe. Interacting with this field is how all the fundamental matter particles acquire mass, according to the standard model. The ATLAS experiment on the Large Hadron Collider is studying the standard model in depth. By taking precise measurements of the particles and forces that make up the universe, ATLAS physicists can look for answers to mysteries not explained by the standard model. For example, how does gravity fit in? What is the real relationship between force carriers and matter particles? How can we describe dark matter, which makes up most of the mass in the universe but remains unaccounted for? While the standard model provides a beautiful explanation for the world around us, there is still a universe's worth of mysteries left to explore.
Okay, and if you're looking for practice with this stuff in particular, try the topic 4 practice assignment posted in the Google Classroom or Agenda. And that wraps up Physics 30. So congratulations, you finished the course. I wish we could have done it together, but what a unique experience for us to share, okay? To all you graduates, congratulations, you worked hard, you earned this, enjoy it. I can't wait to see what you do next. And Marie, I guess I'll see you in September. Have a great summer, everyone. Relax, enjoy. You've earned it. I'll see you around.